And so we could take those healthy individuals and use them as a sort of baseline. We're starting these experiments from a set of healthy sea stars. So that was really kind of the first important point. We then exposed them to the pathogen. And before we actually knew what caused wasting, that meant that we were exposing them to tissue homogenate, so ground up tissues, or in the case of our kind of breakthrough, coelomic fluid. So we started using the internal body fluid of the sea star, which is essentially like seawater. And that's where we see really high abundance of the pathogen. So we would take this coelomic fluid from a wasting sea star, we would inject it into our baseline healthy individuals, and then we would observe and see what happens. And as we would expect, if we're dealing with the pathogen that causes disease, we saw sea star wasting disease from the individuals that we exposed to this coelomic fluid taken from a sick star. So then we use a bunch of genetic or genomic data sets to sequence all of the stuff that's in that coelomic fluid. And it essentially allows us to kind of come up with two lists. So we have one list from all of our wasting sea stars of all of the different microbes. This could be bacteria, it could be viruses, it could be protists, anything that's in those wasting sea star samples. And then we have samples from our healthy kind of control group that never showed disease signs and died of wasting disease. And we use those two lists to kind of say, is there something in these wasting stars that's not in our healthy stars? And that was where we got the first preliminary evidence that Vibrio pectenicida is a causative agent of wasting disease, because we found it in all of our wasting individuals and we didn't actually find it in our healthy sea stars at first. And so then from there, the kind of conclusive, definitive evidence came from actually growing this bacteria. So Amy Chan at the University of British Columbia, she did all of this work where we took coelomic fluid from a wasting sea star, and she actually was able to isolate that bacteria and grow it at high quantities. And then since we had this bacteria in pure culture, which is kind of what the common term we use, we could then expose our sea stars to just that bacteria. So separating it from all the other stuff that you might find in coelomic fluid, just using that bacteria to challenge those healthy sea stars. And we were able to recapitulate sea star wasting disease using a pure culture of that bacteria. And that kind of closed the loop, identifying it as a causative agent.
And now we have 400 stars that we've raised. The oldest one is 5 years old now. There's about 10 of those, and then every age class after that. So we have 4-year-olds, 3-year-olds, 2-year-olds. We have 1-year-olds, and then we have this year's cohort where we have 200 little baby sea stars that we're taking care of right now. And in addition to that, we have to raise the food to feed to them too, because the babies want to be as difficult as possible, and they will only eat in our hands freshly grown sea urchins that we have to grow ourselves. And so we grow those from egg, and that takes about a month. And we grow several thousands of them because these guys are voracious predators, and they eat just a tremendous number of little baby urchins. We were desperate for someone to find this cause. And so, relief and excitement, what I would say would be the two big immediate reactions that I had to hearing that the cause had been found. Excitement because, it's opens up so much possibility, and relief because we've been sort of in this. We haven't been stuck. I mean, we've been talking about how we've been able to make progress in what we're doing, but there's difficulties in running a program where you want to reintroduce stars following a disease that you don't understand. So understanding the disease is kind of key to understanding how you could safely reintroduce them in any kind of large scale way. But what we're most interested in with all our particular goals in our lab as it is now is just being able to test our water, test our stars that we put out in the field, and just be this field site is safe, our stars are safe, we can put them out in the field and they should be okay, at least for now. So those kinds of things. And to make sure that the stars that we keep, we can test our tanks and make sure that we can prevent those kinds of outbreaks that led to the event that we were kind of discussing before. We are really interested in the next stages of restoration breeding for this star. And that would have to be done at either a highly modified facility here at the labs that we don't currently have, or some other location where we can do this in a quarantine kind of setup. So one really important experiment that we're really keen to support is if you take two stars, if you take 20 stars and you expose them to wasting, and you see that four of the stars did, pretty well actually, and four of the stars did terribly, and maybe the rest of them did blah, they got a little bit sick or they got very sick eventually. But if you take those four stars that did really, really well and you breed them together, this is classic breeding strategy. You take two tiny dogs and you breed them together, and you probably are going to make another tiny dog. And that's how we ended up with like ridiculously small dogs and ridiculously huge dogs, right? So it's the same thing with the breeding for disease. If you take two stars that are a little bit resistant and you breed them together, we want to know, does that make a slightly more resistant star than even its parents were?
This is, I think, kind of one of the components of the future work that I'm most excited about. It's so great to see so many facilities now that have the capacity to actually rear sunflower sea stars in captivity. And obviously, the goal there is to be able to reintroduce these individuals back into the wild in areas where they've been lost, and hope that they can kind of create these self-sustaining populations that would have been there 10 plus years ago. And so one of the really kind of exciting and cool things we can do now that we've identified the pathogen is to actually try and identify resistant or disease resilient individuals in sunflower sea stars. So we know that there's some remnant populations that still exist in the wild. It's very possible that over the last 10 years, that has some of those populations may be resistant to disease or more resilient to disease, so better able to kind of cope with it or fend it off. And so what we can do now is start introducing these individuals into our system where we can experimentally challenge them. And then that way we can actually identify individuals that survive exposure to the pathogen. And that suggests that they are resistant or resilient to this disease. And those are the individuals that we want to prioritize in captive rearing facilities.
And that star is recovering now. It's growing its arms back. It's totally amazing.
But we use a probiotic that actually inhibits Vibrio growth. So when they found out that it was Vibrio, that was kind of great news to us because we were like, oh yeah, well we were hitting that already. But basically what we do is for bacterial and stress control, and also just for the water quality in general, we lower the temperature very low on the sea stars. And so they really like to be super cold. The actual ocean's not quite as cold as it used to be. But we've seen in other areas where the sunflower stars were able to get somewhere very cold and deep, those guys tended to survive more during these wasting outbreaks. So that's part of our treatment is we get them very, very cold. So they have to have very good chilling. And so that's step one. That also inhibits a lot of bacterial growth that doesn't like to grow in super cold water. So that's one of the things that we do. We also basically make the environment what the sea star would love to live in, like perfect ideal conditions. So we buffer their water. We use a mix of different minerals and compounds that like are very good for them, and it's what their body's actually made up of inside to essentially kind of give them a perfect little spot to live in where it's like all the water that they're pulling into their body is super clean, super like ideal for what's great for them.
So one thing I think that would be really great to do, that we're certainly keen on doing, hopefully collaborating with Tiffany, is to actually test that with individuals that we know have been exposed or infected with this Vibrio pectenicida pathogen. Because sea stars, they're this really interesting group of creatures. They only have so many ways of responding to stressful conditions. And so what we want to do is make sure that she's used her protocol. Lots of people have used it, and it works. But we want to actually make sure that those sea stars that protocol is treating are actually positively infected with our pathogen. Because then we can kind of firm up those details and say, like, yes, we're confident that this protocol works for individuals dying of sea star wasting disease.
There's a lot to still do. I mean, it's exciting now that we have the cause in hand, so that it opens up a lot of possibilities. But there is a lot of stuff to do. I mean, we need to continue to optimize. We haven't figured out everything about breeding, and we need to optimize the breeding. We need really, really large scale breeding facilities up and down the coast, especially in places like California, where the problem is the most dire. We need to be raising thousands and thousands and thousands of sunflower stars for potential release. We need to be doing these experiments, looking at their resistance to disease, and hopefully releasing stars that are more resistant into the wild. And then there's a whole bunch of field studies. We strongly suspect that, and we have some data from modeling to back this up, and some experimental data that suggests that sunflower stars can protect kelp from urchin overpopulation. And we saw when the sunflower stars disappeared, the urchins got overpopulated, and the kelp really got hammered by too many urchins. And so having the balance in the ecosystem with the right number of sunflower stars can keep the urchins in their normal numbers and then keep the kelp healthy. And so, we need to do more field experiments to really demonstrate this. A really big, sea star that people are familiar with, I mean, probably worth trying to save. But this one in particular has got kind of, the more we find out about it, the more we find out that it's got sort of really, really outsized ecological importance. So we're doing more here than trying to just save a sea star, which is a worthy cause in itself, like I said, and is important. But we're trying to save entire ecosystems. We're trying to protect the entire Northeast Pacific fundamental ecosystems.